Now, looking at some problems on the conical pendulum, we've got the first one here, which is we've got an inextensible string, which means that it won't extend. So that's got nothing to do. It's going to be a fixed length. So it's 2 meters. So the string goes from A to B here at 2 meters, and has a particle of mass 3 kilograms at that, and it's rotating in a horizontal circle, which is 1 unit below, 1 meter below the position A. So there's the circle's rotating around there, 1 meter there. So we want to find the angular velocity of the particle and the tension in the string. So what we basically got to establish, we've got the tension going up in the string. We've got mass times gravity, so that's where the 3 times g comes from, because mass is 3. So opposing that, if that's going to be theta, that's theta, that one's theta there. So I've just put y here and tried to use a vector v to establish that this would be equal to t cos theta here for our tension that's acting vertically. So the forces that are acting vertically here, that's opposing 3 times 3g, would be t cos theta, and acting this way would be the t sine theta. So that's what we're getting there. So resolving them horizontally and vertically, that's what we're getting there. T cos theta that way and t sine theta there. We can also establish that r is going to be root 3, because we're going to use Pythagoras' theorem. So r is square root of 4 minus 1, which is root 3. We also then can see that cos theta is going to be half, because it's adjacent on the hypotenuse, and sine theta is going to be root 3 on 2. So we've got values for cos theta and sine theta. So when we establish vertically that t cos theta is equal to mass times gravity, or t cos theta is 3g, because they're acting and opposing each other, so 3g there is equal to t cos theta that way. So when we have that, we know cos theta is equal to a half, and that's 3 times gravity. So tension must be 6 times gravity newtons. That's the tension in the string. We also know that horizontally t sine theta is equal mass times omega squared times r. Well, mass is 3 and the radius is root 3. So we've got sine theta is root 3 on 2. So the tension we've got, sine theta we've got, we can then have an equation with just omega in there. So 6g times 3 root 3 on 2. 3 omega squared root 3, so we can start cancelling root 3s. We can start cancelling the 6 with the 2, and that gives us 3, and then the 3 cancels with the 3 there. It leaves us with omega squared is equal to gravity, or omega would equal to the square root of gravity radians per second. In question 2, we've got number of revolutions per minute increases in a conical pendulum. So we've got moving in a slower one, it'd be 30, so think about what happens to the bob here as it starts to spin faster. It's going to move that way. So we want to move it from 30 revolutions a minute to 45 revolutions a minute. So what it's going to move there, we want to look at what the change in the height would be there. So if that's the height there and the height there, then if we get the difference in those, we can see that we can get a height there would be given to that, and then find the rise and the level of the bob there. So we can show that and then find the rise and the height of the bob. So vertically, what do we know? We know that t cos theta is acting that way both times. So it's going to be equal to mass times gravity, because mass and gravity is going to stay the same there. And we get t sine theta is acting inwards, opposing to the mass omega squared times r. So dividing these two, so divide this one by this one, the t's cancel, sine on cos gives us tan, mass cancels, and we get omega squared r on g. We do know as well that from the triangle here that we can, from either triangle, we've got the radius there, we've got the height of our bob, well, the circle above from the top there, and well, that would give us r on h. So tan theta is equal to r on h. So we can start to establish that h on r is equal to gravity on omega squared r, because we can flip that one, so we flip that one, and then we can cancel our r's and get h be equal to gravity on omega squared. So there's our result there. So if it's 30 revolutions per minute, well, 30 revs per minute, well, every revolution is 2 pi radians, and if we want to work it by seconds, in seconds, which is what we want our angular velocity to be, that would give us 60, divide by 60, so that gives us pi radians per second. So there's our angular velocity when we've got 30 revolutions a minute. So we get g on omega squared, and omega's up pi, so we get g on pi squared. 45 revolutions per minute, well, we multiply by 2 pi and divide by 60 to give us 3 pi on 2 radians per second. And we sub that in, we get 4g on 9 pi squared. Do our subtraction, gives us 5g on 9 pi squared. This time we've got a hemispherical bowl, so it's a hemisphere, rim's horizontal. We've got a particle of 90 grams. Describes a horizontal circle inside the bowl, 140 revs per minute, and the internal radius of the bowl is 20 centimeters. 20 centimeters, so 0.2. So it's not actually that. That should be 0.2 meters there. So we want to find the depth of the circle below the rim when it's at 140 revs a minute, and determine the reaction between the bowl and the particle. So what's happening there? So we know that we can get the mass as 0.9. Omega is 140 revolutions a minute, which can come down to 14 pi on 3 radians a second, and gravity's 9.8. So we've established that. Notice we're putting it into kilograms. So what are our forces going to do? Well, we know again that if we've got a reaction going against the bowl there, back up towards the center of the circle, or center of the hemispherical bowl, we've got a reaction force there. We know we've got mass and gravity acting there, so that would be r cos theta. So if that's r cos theta, that would be equal to mass times gravity acting there, because we've drawn a right angle triangle in that one, in that point there, because that would be, if we had theta there, if you're wondering where the theta come from, well, theta would be normally there, because that's the angle that's going from the center, and so that would be alternate. Cos theta could be written as m times g on r, and we know mass, we know the gravity, and we've got r there. So we've got cos theta is equal to that. We can also sum the forces horizontally. We know what's acting towards the center, be r sine theta. So that'd be r sine theta acting inwards there, opposed to mass times omega squared times r. So we know from this as well, if that's the radius of the circle that's being generated, that's the inner radius of the bowl, so that's the distance from the center of the bowl to the outside, to the circumference. That's 0.2, 20 centimeters, and that's the height that's going to be generated there. Then we can start to get that sine theta would be r on 0.2, so that's where that one comes from. So we can get r is equal to 0.2 mass times the mass times omega squared. We know what the mass was, we know what omega squared was, so there's our reaction force, 0.392 pi squared newtons. So that's the reaction force that's acting against the bowl. And we also know that from this that cos theta would equal to h on 0.2. So we can get h is equal to 0.2 cos theta. We know what cos theta was then. We've just found out what r was. We can set that in, put all those values in, and calculate our value of h there. So there's the first few problems. Notice what we're doing. We're getting these forces, summing them horizontally, we're summing them vertically, and we're using our ideas and our formulas to actually get solving the problems that we need to, getting the forces, values of the forces, or heights or radii, whatever we need in these situations.